Hello, I'm Douglas Platt, and this is my sample lesson on propositions and truth values. A proposition makes a claim, either an assertion or a denial, that may be either true or false. In fact, it must be either true or false. The logical statements have no gray values, and they must be presented as complete sentences. The negation is the opposite of, or is forming the opposite of, a proposition. Since the values of a proportion or of a proposition can be either true or false, then the negation, represented by not P or tilde P, and its truth values are always opposites. Okay. So if we use a symbol P to represent the assertion, not P or tilde P is its negation. So if P is true, not P is false. If P is false, not P is true. And we have the double negative, which uses one negation to modify another negation. Not P. So if P is true, not P is false, then not P comes back to being true. Logically. Even if intuitively or grammatically P and not P are generally not treated as exactly equivalent. For example, it's sunny out and it is not raining out don't mean exactly the same thing. The and statement, or the conjunction, takes two statements, and most of our logical connectives take two statements, generally labeled P and Q, but they can represent anything. And this is true only when both P and Q are true. Roads freeze up when they are wet and below freezing. And since we have two things going in, we have P and Q, we end up with a total of 4 cases. And anytime we have 4 cases, they're represented in the same order. True, 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 false, false, true, false, false. P and Q is true when both are true. True, false gives us false. False, true gives us false. And false, false gives us false. And you can determine the truth value of any compound statement by matching the truth value of the two statements that go into it with the final value in this left column. Okay. The logical or statement, or the logical disjunction, uses the two different definitions of or. Inclusive, which is either or both. If I go to a burger place that has fries and onion rings, and someone asks, do you want fries or onion rings? I can say, yes, I want both. And it makes sense. That's an inclusive or. An exclusive or is a statement that you can have one or the other. It is either dry or raining. Generally in logic, we assume the inclusive or unless we have a reason to suspect otherwise. or is true as long as at least one of our proportions are true. So if we have P and Q again, P or Q gives us a true. A true or true gives us true. True or false also gives us true. False or true gives us true. But false and false, or false or false, gives us false. So I don't have any food allergies. So if the food has peanuts and wheat, I'm fine eating it. If if a restaurant's menu has peanuts but things without wheat, my wife can eat it. Something has no peanuts but wheat, a friend of ours can eat it who's allergic to peanuts. If the restaurant has neither peanut-free nor gluten-free food, we're looking for somewhere else because it's a false statement. Okay. The conditional statement is among the logically more powerful ones. And it is an if something then something else, where we have antecedents, P, leads to the consequent, Q. If P then Q, if you turn on the oven, then it gets hot. Okay. And we have 4 cases again. If P is true, then Q is true, then it is true. A politician claims that if elected, she'll raise the minimum wage. If she gets elected and she raises the minimum wage, then her promise is true. If she's elected but does not manage to change the minimum wage, then she broke her promise. If the statement is, or if she's not elected, then her promise is exempted, whether the minimum wage is raised or not. Okay. With conditional statements, we have 4 major variations. The original case, if P then Q, if you vote, then you can complain about who is elected. Okay. The converse is if you can complain about who is elected, then you can vote, if Q then P. The inverse, if you don't vote, then you cannot complain about who is elected, if not P, then not Q. And what we call the contrapositive. If you cannot complain about who is elected, then you cannot vote. Any 2 statements are logically equivalent, or any set of statements is logically equivalent, when for every truth value they have the exact same statement. Anywhere that one statement is true, or for any case that one statement is true, the other one is true. For any case that it is false, the other one is false. The conditional and contrapositive statements are logically equivalent. The converse and inverse are logically equivalent. So, if you vote, then you can complain about your politician, is logically equivalent to if you can't complain about your politician, then you cannot vote. And we can collect all of these into a single unified truth table, as is shown here, where You can look for the values for P or Q, or the before statement and the after statement. And whichever pair you need matches with the next line over. So, if a restaurant serves bacon and sausage, then you can choose bacon or sausage as part of your meal. So if we let P equal bacon and Q is sausage, then we have P and Q. If P then Q, then P or Q. In our first case, we have true and true for P and Q. So we have first step is to identify our four cases, and we replace each letter or each variable with its truth value for that associated case. So anywhere we have a T or a P, we put a true or a false as shown by the particular cases. With Q, true, false, true, false. Next, we want to use our AND statement. So we're going to be looking for our P and Q. So true and true, we know is true. True and false, looking at our truth table, shows us true false is false, false true is false, and false false is false. And we can look at our OR statement. This column here, whenever we have both are true, then we have a true. True or false, we get a true. False or true, true. False and false is false. One thing to keep in mind when we're dealing with truth tables and the like, it's not a matter of memorizing them or going with instinct necessarily. It's a matter in large part of knowing where to look to work through and think through the problem. And for this kind of problem, the truth table is the reference you go to. At this point, the original truth value of the cases is no longer relevant. So we can get rid of anything that I wrote up here in brown, and we're down to these pairs of cases. So we're going to use the if then statement. If true then true is true. If false then true is true. If false then true is still true. If false then false is true. And we have what's called a tautology, a logical statement that is always true.